It's time for the exercises for lesson 1.4, which has to do with absolute values. So these are what I'm going over. This is an OpenStax Precalculus 2E. I recommend you try them and then come back to the video where we will go over the solutions. Well, let's get started. 11 and 12 are similar. We are solving equations that have absolute values in them. We have to remember there's two possibilities for both of these, really. I will do number 11 first. Absolute value 6 minus x is 5. Well, one possibility is 6 minus x is 5, but another one is 6 minus x is negative 5. And then we can just solve for each x value that we get. Let's see. I will subtract 6. We get negative x is 5 minus 6, which is negative 1. And then when we divide by negative 1, we get x is 1. So this is one solution. Then the steps are very similar in the other case. First, let's subtract 6 from both sides. We get negative x is negative 11, and just divide by minus 1. We have x is positive 11. This is the other x. So we have two solutions in 11, and we will also see two solutions in 12. Here, one possibility is 5x minus 2 is 11. One possibility is 5x minus 2 is negative 11. Here, 5x equals 11 plus 2. We get 5x is 13. Now just divide by 5. X will be 13 over 5. We have a fraction. It's fine. I would leave the answer like this rather than converting it to decimal, say. The other one, similar steps. Let's add 2. 5x is minus 11 plus 2, which is negative 9. And once again, we divide by 5. We get x is negative 9 over 5. This is the other x value that solves this equation. Now we move on. 25 and 26, we will find the x and y intercepts for the graphs of each function. We did one like this in the lesson video. Here are two examples to practice. The y-intercept we will do first. I find it a bit easier. We just need to evaluate the function at 0. We get 2 times the absolute value of 1 minus 10. This is just 2 minus 10. This is negative 8. As a point on the graph, this point is 0, negative 8. Let's underline this. Maybe I will write above, this is our y-intercept. Great. Now for the x-intercept, which here, as I mentioned in the lesson, there's no more than one y-intercept, but you could have multiple x-intercepts. Here we set the function value to 0 and solve for x. So set 0 to be 2 absolute value of x plus 1 minus 10. We get, let's see, add 10 to both sides. We get 10 equals 2 absolute value of x plus 1. Maybe I'll take one more step, divide by 2. So when I do this, I get the absolute value of x plus 1 is 10 over 2, which is 5. Here's where I can break this into two cases. Either x plus 1 is 5, or x plus 1 is negative 5. And here we can just subtract. We get x is 4. Here we get x is negative 6. But let's write it as ordered pairs. So we have 4, 0, and we have minus 6, 0. We have two x-intercepts. These are x-intercepts. 26. It's similar, but we're also going to find out it's different. So this is a great problem. First, as before, y-intercepts We evaluate the function at 0. We get 4, absolute value of minus 3 plus 4. This is 4 times 3, which is 12, plus 4. We have 16. X-intercepts. Oh, let's write it as a point. This would be 0, 16. Okay, wonderful. This is my y-intercept. Now we move on to the excitement of this problem, which is the x-intercept. So let's set my function equal to 0 and see what happens. We set 0 to be 4, absolute value of x minus 3 plus 4. We can proceed very similar to above. We can subtract 4 from both sides. We have negative 4 is 4, absolute value of x minus 3. You might already see an issue, but I will take one more step before I make a comment about the issue. Let's divide both sides of the equation by 4. When I do, I get negative 1 equals absolute value of x minus 3. Here's where we realize we have no x-intercepts because the absolute value is negative, never negative. This is our problem here, this part. The absolute value, I will just write the range of this function, and I'll write it with the x minus 3, would be closed 0 to infinity. And in particular, the absolute value is never negative. I like this example because it makes us think about the range of the function. 32, we want to solve an inequality and write our solution in interval notation. We have two possibilities I talked about how to solve something like this, because geometrically, this says we want all x values that are at least 8 away from 4. That's what this is saying geometrically. So you could either solve with a number line or use properties of the absolute value. Maybe I'll solve using properties. What this says, well, there's two possibilities. One is that x minus 4 is bigger than or equal to 8. And the other possibility is that x minus 4 is less than or equal to minus 8. This or this is equivalent to this inequality with the absolute value. So we can just solve each one. This one says x is bigger than or equal to, just add 4, 8 plus 4, which is 12. And this one, once again, we can add 4, it says x is less than or equal to minus 8 plus 4, which is negative 4. This is x bigger than or equal to 12. This is x less than or equal to minus 4, and we want an or. So we can write this in interval notation. It will be a union. The first one is here. This interval is negative infinity to negative 4, and it's closed on this endpoint. Then we put union, and we want this interval, x bigger than or equal to 12. So it's closed at 12, and then goes to infinity. This is our answer to 32. Now the last one, we want to graph an absolute value function. The main way I want to think about this is, I want to think about this function as a piecewise defined function. This is going to be the way you really want to think about these quite often, at least in your calculus courses. So let's recall absolute value of x as a piecewise defined function. It's x if x is bigger than or equal to 0, and it's minus x if x is less than 0. To get the absolute value of x plus 1 as a piecewise defined function, I could make a number line as we did in the lesson video for the absolute value of x squared minus 4. This one, though, is a little bit simpler than that example, and so I'm going to go about a little bit shorter of a way. Okay, well, if I want the absolute value of x plus 1, let's just replace x in this formula by x plus 1. this would be x plus 1 if x plus 1 is greater than or equal to 0. And, well, multiplied by minus 1 would be minus x minus 1 if x plus 1 is less than 0. But now you see I have these two inequalities that I can just slightly translate. The first one says x is bigger than or equal to minus 1. The second one says x is less than minus 1. And this is what we see here. So this is what I'm going to use on the next page as a piecewise definition for the absolute value of x plus 1, and then we can graph. So at minus 1, the function is 0. That's the easiest point to graph. But if you're bigger than or equal to minus 1, it's a line with slope 1 and intercept 1. So in particular, it goes through this point, it goes through this point, it goes through this point. You see, over and up, over and up, over and up. I really like this activity. We are thinking about how do you graph lines? How do you think about a piecewise defined function? But then our new absolute value. So that is a great way to end this module, is with this example. Here is the graph for x bigger than or equal to minus 1. But then for x less than minus 1, if you look at this, you see it's a line with intercept minus 1, slope minus 1. So the intercept, while this is not a part I should keep in the graph, it's down here, right? So slope is minus 1, which means this is on the graph, this is on the graph, and this is on the graph. Looks like this. Now, you could have graphed this just by doing an operation on absolute value, because we know the shape of absolute value of x is like this, and this just shifted it over 1. But I purposefully wanted to think about this function as a piecewise defined function and graph it that way because it's a great exercise. So this is the end of these exercises for lesson 1.4. Thank you.